In this video, I'll demonstrate a method to get to the solution to all parts of the question that's alternative to the ICF table. I've written out all of the given information, including the balanced chemical equation, the amounts of manganese and hydrochloric acid that were given to us, and the enthalpy values. So you can see that the delta H, the enthalpy or the heat of reaction, in this case is a negative value, which tells you that energy is given off. It's an exothermic reaction. Now the first thing I'm going to do is calculate the number of moles for each of the reagents. And I'm also going to read down to the bottom of the question. In part C, we're being asked for the amount of hydrogen gas that's formed in this reaction. And that's the one I'm going to use when I figure out my limiting reagent or limiting reactant. So first things first, I'm going to work with what I've got. So for manganese, we have 115 grams of manganese, and using your dimensional analysis, you're going to say grams of manganese, and we want moles of manganese. When you consult your periodic table, you'll see that the molar mass of manganese is 54.95 grams in 1 mole. And when you do that calculation, you're going to end up with 2.093 moles of manganese. And this is what you're initially given in this case. Now let's look at the other reagent, the hydrochloric acid. In this case, we're not given a mass, we're given the concentration and the volume. So I'm going to start with both of these values. I have 3.50 molar, which is the same thing as moles of hydrochloric acid per liter, 1 liter of hydrochloric acid. And the reason I wrote it that way is so that the dimensional analysis becomes really easy instead of memorizing formulas. And I should have crossed these guys out. I'm going to cross this one out. And when you do the math involved in this calculation, you'll get 4.375 moles of hydrochloric acid. Now I'm going to answer basically all of the parts of the question by going through the calculation of how much hydrogen gas would be formed for each of these starting amounts. And in part C, it asks us the theoretical mass. So I'm going to go all the way to the mass. So again, I'm going to set this up with 2 separate equations, figuring out how much hydrogen gas is produced with the amount of manganese that I have, and then also with the amount of hydrochloric acid that I have. So you can see the power of the mole in each of these cases. Note also that I'm not rounding off really at all for sig figs until the end of all of this. So we have 2.093 moles of manganese, and I want to go from moles of manganese, so here I'm using my dimensional analysis again, to the moles of hydrogen gas. And I chose this one because part C is asking about hydrogen gas. Now the numbers that you fill in, I've handled the dimensional analysis here, but the numbers that go in this expression, this second expression, are determined by the balanced chemical equation. And you can see that 1 mole of hydrogen gas is formed by 1 mole of manganese. Now we could figure out the moles here, but I'm going to go all the way to the mass because then I'm answering part C as well. And this is really efficient. So I really want to figure out the grams of hydrogen formed. And note that hydrogen is a diatomic, so the molar mass is 2.02 grams per mole. When you work out this math, you get 4.22786. Again, I'm not limiting anything for sig figs until I'm happy at the end, okay? I need to know which one is limiting first of all. Okay, so now we do a similar calculation starting with the moles of hydrochloric acid. So 4.375 moles of hydrochloric acid. And once again, we're going to cancel out moles of HCl, and we're going to figure out how many moles of hydrogen gas are being formed. The only way you can compare these for limiting reactant or limiting reagent is to make sure you're considering the same product. You don't change to manganese to chloride and calculate that one. You have to consider the same product, okay? Now let's look at the molar ratio for these ones. It says that 1 mole of hydrogen is formed by 2 moles of the hydrochloric acid, and then I'm going to go all the way along to figure out the mass of hydrogen formed by this reaction. So we have the same 2.02 grams per 1 mole, and I should be doing my canceling all the way along just to be really consistent. Now we do the math here, and you can see that we get 4.41875 grams of hydrogen. Now, how do you figure out the limiting reactant or the limiting reagent? It will be the one that produces the smallest amount of hydrogen. Okay, think of this as if you were baking and you were limited by the number of eggs that you had. If you were working out your recipe based on the number of eggs you'd have, then it's going to be the smaller amount of cookies that you can make. That's one of the ways to try to keep this straight in your mind. Okay, so now I'm going to use my handy dandy highlighter to show you that the smaller amount produced is the 4.22786 grams of hydrogen, which means that we go back to manganese and we can label manganese as the limiting reactant or limiting reagent. You can call it either. And we also know, now we should use our sig figs, we also know that and this one had 4 sig figs, 4.228 grams of hydrogen are going to be formed. So you can also answer part C of this equation. Now they've limited it to 3 sig figs based on the molar mass, but you would not do that. You base your sig figs on the measured quantity, not on the molar mass that you get from the periodic table, because different periodic tables have different rounding of the decimal places. So the theoretical mass asked for in part C is going to be 4.228 grams of hydrogen. And then in part D, we're given what actually happened in this reaction. So we are told that at STP, 33.6 liters of hydrogen gas were formed. And so you have to note that we are given these conditions, STP. This is an important distinction because we can use the molar volume of a gas. This is a special case, and we can calculate the mass of hydrogen that was formed. So we've got 33.6 liters of hydrogen gas, and we know that at STP, we're using our dimensional analysis, the volume of a gas at STP, any gas at STP, is 22.4 liters in 1 mole. And then we can further go on to figure out the mass of hydrogen that was formed by using that trusty molar mass that we always go back to. And let's cancel our moles. And when you do the math here, you'll get 3.03 grams of hydrogen. This is the actual yield. Okay, that's how much actually was produced in this reaction, because reactions are rarely perfect. We usually lose something either to the environment or elsewhere in the reaction. So the percent yield, and you were given a formula for this, is just the actual yield divided by the theoretical yield, which we calculated above. This is if all situations were perfect. And then we multiply by 100%. So this is just like figuring out your percentage on a test. Okay, so we actually formed 3.03 grams of hydrogen, and theoretically we could get 4.228 grams of hydrogen, and then multiply by 100%. And your percent yield, using the correct sig figs, is 71.7%. Okay, so this is going to be limited by the 3.03, and I've used more digits based on the original that I explained above. So this differs from the answer on the answer key by 0.1%, but this is well within acceptable.